laboratory, and it wasn't so easy because I don't speak Portuguese. But we are still in time, so I promise you that we will finish earlier, so we are still in time. Okay, so we will continue with UML SysML, and then now comes a general overview, and then we continue with going into the details. So I will start with UML. That is actually a modeling language, mainly for software engineers, but not only for software engineers. Just the first question, just to practice a little. Who have ever heard about UML? Please raise your hand. Who didn't raise their hand? Okay. And there are some people who didn't belong to any category. Okay, so it's a modeling language. It has a very long roots actually. It is the abbreviation for Unified Modeling Language, and it's a standard by the OMG, by the Object Management Group. So the first initial version comes in the 90s, and now we are at the 2.5 version, and so it has a very long history now. Actually, this is the history. So it started in somewhere at the really end of the 80s with the definition of state charts that were defined in a paper by Harrell. And because they recognized that it's very nice to have formal models, but the problem is that they are not so easy to be used. So we need something that helps, that supports the engineers in the modeling and in the design. So he just invented state charts in that time, and after several steps, we just reached the UML standard. And from UML, there is a branch of SysML. So as you will see, SysML came out of UML. And there is another direction that is worth mentioning that goes here, is so-called XUML, executable UML. So some companies and some organizations wanted to have a UML, a design tool that is executable, and you can generate code directly from your models, and that is this XUML standard. And there are some tool support for that. There are some companies who use it, but it is actually, this language is not so user friendly. So it is not, and that's why it is not as popular as UML. So there are some related standards we have to mention and you have to be aware of. One is this MOF, that is the Meta Object Facility Core. That is a modeling language for defining modeling languages. We will talk also about a little bit about OCL, that is Object Constraint Language. That is a textual language for formulating constraints and queries over models. We will learn how to use it, and you will see some examples. One extension of UML is FUML. That is the foundational UML that provides a semantics for a foundational subset of UML models. And these UML models are executable. So you can execute them and you can directly generate code from them. So the goal was to extend UML with all these capabilities. And ELF, that is an action language for FUML. And there are some other representation and standards related to UML. Let's go into the details. What is the taxonomy of UML? So in my former presentation, I mentioned you that you want to model structured data, but you also want to model the behavior of the system. And UML provides support for both of them. So here you can see the structural description languages provided by UML. You can use them to develop models of structure, of data, components, and everything else. So you can use the class diagrams, component diagrams, and object diagrams, and the composite structure diagram, deployment diagram, and also the profile and package diagrams. So these are used for the structural representation. And UML supports also the description of behavior of some execution of our system. And you can use activity diagrams, use case diagrams, state machine diagrams for this purpose. And you can also model the interactions in your system. And there are various kinds of interaction representation in UML. One is sequence diagram, another is communication diagram, interaction overview diagram, and timing diagrams. So this is the main UML diagram taxonomy. And let's continue with SysML. That is a modeling language mainly for systems engineering, but not only for this purpose. So at first we have to define systems engineering. Systems engineering is a multidisciplinary approach to develop balanced system solutions in response to diverse stakeholders' needs. It's kind of integration engineer because we have some parts that are related to software engineering, hardware engineering, mechanical engineering, safety engineering, and security engineering. So as you could see, for example, in a car, many areas contribute to the development of a car, of a railway, of a missile, or everything else. So you can consider systems engineering as a kind of process engineering, and there are many systems, there are many fields where you have to use this kind of systems engineering approach. For example, airplane, car, aviation, railway, or even when you develop a notebook, because it has also many physical and electronic and other parts. And SysML can be said to be a UML for systems engineering. So SysML supports the specification, the requirement design, the analysis, verification, validation processes of various kind of things such as hardware, software, data, procedures, and so on. SysML is also developed by the OMG and also the International Council on Systems Engineering. It is in COSE, that Iconics approach I showed you before, that is also developed by this council. And in 2020, we had the version 1.5 actually. And you can find more information in this web page. And how do they relate? How do UML and SysML relate to each other? UML has many diagrams and languages. There are some that are not used by SysML, and there is a subset of UML that is absolutely the same in SysML. And SysML extends UML with new diagrams and new things. So how can you imagine this? So these are the main diagram types of SysML. You can describe your structure with the help of block definition diagrams, internal block diagrams, package diagrams, and parametric diagrams. You can describe the behavior with all the diagram types that we learned, that we saw in UML, and also you can use requirements diagram. How does it relate to UML? Actually, SysML modified some diagrams of UML, because such as this block definition diagram and internal block diagram, they are a modification of some diagram types of UML. And also there are some extensions to activity diagrams, especially to support the industrial process design. So if you have, let's say, factory and PLCs and everything else, then SysML extended activity diagrams to support the modeling of such systems. There are new diagram types, such as requirement diagram, that is not in the UML, and the parametric diagram is also an extension. And there are some diagrams that are completely the same as in UML. So you only have to learn it once. So these are the main diagram types, and as I mentioned, SysML targets many aspects of the systems engineering, so starting from behavioral modeling and static aspects, but it also supports the development of requirements and provides languages for that purpose. And let's continue with some more details about SysML. In SysML, each SysML diagram represents a model element, and each SysML diagram must have a diagram frame, as you can see here, and the diagram context is indicated in the header. So if you will use a SysML editor, and hopefully you will use in your work, then you will just see the diagram kind, the model element type of the diagram, the model element name, and some diagram description. So that is how we start the modeling with SysML. Actually, as I mentioned there are various kind of diagrams: package diagram, block definition diagram, internal block diagram, parametric diagram, use case diagram, activity diagram, sequence diagram, and state machine diagram. So you can use these diagram types. So as I mentioned there are many common diagrams in UML and SysML. There are some extensions of UML that are implemented in SysML, and there are also some new diagram types in SysML. And the basic thing in both language is that you start the modeling with the help of packages, and you can use package diagrams in both in UML and also in SysML. So package diagrams are about they try to answer the question that how to organize your models, your system description. So package diagrams and packages are used to group elements in your system. So it provides, these packages provide a containment hierarchy for model elements. It's quite similar to the directories in your computer. You put your files into directories and try to organize your files according to this. Actually, sometimes I forget it, and that's a huge mess in my computer, but be more clever than me. So, and it also provides a namespace for the grouped elements. So it provides a qualified name. So for example, here there is the system of cyber physical agricultural system. It's in this hierarchy, and its name, its qualified name is provided according to this containment hierarchy. So you can identify and you can reach the elements through this name and through this hierarchy. That is what is important here, is that packages are not for modeling real world entities. So it's just used for organizing your model. There are special packages that we have to mention. One is the profile package in UML that extends, that you use to extend your meta model. And actually this is also used, they used it to define the SysML language. And there is also the model special package that will contain the elements of the domain of interest. And you can also use model libraries in SysML that contain the reusable model elements. For example, here you can see the primitive value types are provided as a library for SysML. So you can have also some relations between packages, such as containment. So one package can contain other packageable elements and other packages. You can import packages. In this case, you import all the elements from another package to a namespace. Actually, if you remember this SSOT paradigm, this also supports the application of this paradigm, because this way you can just reference another package that is developed by another developer. And you can also import elements from one package to another. And packages have this frame with the name, type, and all the other information. And here you can see our first package that has a name, and it can contain other packages that you can depict with this compartment relation, that you put the other package inside. But you can use another notation for this. So this is another contained package inside this package. So there is two different notations for containment. You can import packages, and you can import also elements into your package. So as a summary, with packages, we will group model elements hierarchically. It will provide namespaces for model elements, and packages are about how to organize the models and not for real modeling purposes. And now we will continue with requirements. So with requirements modeling, and we will learn not only the requirements modeling language, but some other best practices to be used in the development. So as I mentioned this is the first step in the platform-based systems design. So you start by defining the requirements of the system. So now we will go through about the roles and challenges of requirements engineering. We will write hopefully precise textual requirements, and we will see how we can capture requirements using the SysML language. I will also show you the concept of traceability, that is an often used concept in especially in critical systems, and it is required by the standards in many cases. And we will also see how one can use cases to understand the system and describe the basic interactions. So but let's start with, why do we need requirements? If you start a project and you start to develop something, actually there are many things you have to consider. So there is always a business case. So why do we need this project? Why do we need this these things? There are some constraints regarding time. You also have to provide some glossary. I have formerly mentioned that you need a glossary, and you have to collect the existing document standards, identify experts, prepare inventory. You have to identify teams and the context. And finally, you have to create your requirements. In systems engineering, in development, there are many teams collaborating uh, to be able to support the development. So you have the customer team with stakeholders, and they want something. And there is the development team with all the engineers, software engineers, hardware, computer, and so on. They will implement the features, and they these teams have to collaborate, have to work together in order to reach the goal, the common goal. And there are various kinds of communication between the teams. So there are many just here, and it is great if you have, for example, face-to-face meetings. That is very efficient, but unfortunately it has a large overhead. So you have to support all these this communication with some modeling languages. And for example, at the early stage of the development, when you communicate with your customers, the requirements are the key point to support this. So what is a requirement? I provided here two definitions from two big companies. So one is that a condition or capability a system must conform to. This definition is provided by IBM. There is another definition, is that the statement of the functions required of the system, and this definition is provided by Mentor Graphics. And each requirement needs to be at first identifiable and unique, so we need unique IDs. It has to be consistent. That means that our requirements shouldn't contain contradiction, and our requirements have to be unambiguous. They must have only one interpretation, and it is good to have verifiable requirements. That means that you can test. You can just assign tests for your requirements, and if these tests are successful, then you can say that my requirement is satisfied, is fulfilled by the system. And requirements are usually captured with special statements and vocabulary. As I mentioned, requirements and also play a key role in critical systems, and you will need them also from the certification perspective. So these are the concepts from the EU standard, that is a standard used by the avionics. So maybe those who will work at Embraer, you will have to learn about that. And this standard divides the requirements and the artifacts during the development into these parts. So at first you have the high-level requirements that are customer-oriented, and they provide a black box view of the system, so you do not see inside your system. And it is usually captured in a natural language. But from the high-level requirements, you can do the derived requirements, where you can capture design decisions, and you can actually you can derive from the high level and also from low level requirements. So in the lower level requirements, you define those things that you need to support the implementation and reaching the source code. And also derived requirements appear at this level. From the high-level requirements, you also have to create the software architecture with interfaces, information flow, and so on. And from these requirements, you create the source code and the executable object code. And what you have to provide is traceability during the whole process from each level to each level, and that's very, very important. And we will try, we will learn how one can do it with the help of SysML. So what kind of requirements we have? We have functional requirements that are the core, that define the core technical goal. And we can have also extra functional requirements such as performance, dependability, safety, and security related requirements. For example, core technical requirement, a functional requirement, is that the train shall close its doors upon remote request by the operator. That's a functional requirement. But here is an example of performance related requirement. For example, the closing of doors should take no more than 4 seconds. Or a dependability related requirement is that the mechanism operating the doors shall endure 5 years of continuous operation without maintenance. A safety related requirement is that the door must never hurt the passenger when closing. And the security related requirement is, for example, a secure cover shall protect the mechanism against vandalism. So so now you can imagine the different requirements that you can express. And the main difference between functional and extra functional is that functional requirements are usually specific to a given component. Yeah, sure, at the beginning you will have system level requirements, but you will just decompose your requirements in a way that after you will provide requirements for the individual components. Extra functional requirements on the other side must be fulfilled by the system as a whole. So, for example, safety and reliability requirements can only be fulfilled by the whole system. So, for example, in avionics, in an airplane, we want that we are not interested in the safety and the reliability of the individual components, because we are only interested in the system level reliability, because that represents that how many people will die in our system because of our system. And as I mentioned, between the different kind of requirements, you have these derivation rules. So, for example, customer high-level requirement, safety requirement is that the door must never hurt the passenger when closing. And from this, we can derive a functional requirement at the high level, that the door must be able to detect obstruction. And this way, we can ensure the fulfillment of the customer requirement. It's very important to talk about how to write requirements, good practices and anti-patterns. So textual requirements usually contain a short description of the problem and not the solution. If you use English language for that, they used to follow this pattern, that we start by a subject, then comes an auxiliary verb, the object, and conditions. For example, here is an example that the railway operator shall create a direct route between any 2 points on the track. It's very important, if you design requirements, to be precise. So quantitative is better than qualitative, and avoid passive sentences. And use of auxiliaries in the positive case, shall and must has a priority over should and may. In the negative case, must not is stronger than may not. So this way you can specify priorities. And there are some examples of the various requirements. Functional requirements are that the operator shall be able to change, to change the direction of turnouts, or the terrain equipment shall periodically log sensor data with the timestamp. A safety requirement is that the system shall ensure safe traffic within a zone, or no single faults shall result in system failure. Performance related requirement is that the system should allow 5 trains per every 10 minutes. Dependability requirement is that, for example, the allowed downtime of the system should be less than 1 hour per year. You can have supportability requirements that the system shall allow remote access for maintenance. Security related requirement is that the system shall provide remote access only to authorized personnel. And usability requirement is that the user interface should contain only 3 alerts at a time. Actually, this is a very important requirement in many cases, because there were very serious accidents because the too many alerts appeared, for example, for the pilots in planes. So you have to pay attention to this. And there are some anti-patterns we will go through. So what is the problem with this requirement that says the system should be safe? And it's a question for you. So I will just ask somebody at the last row to help me. What is the problem with this requirement? Yeah, please. Can you help him? Anybody? So the problem here is that it is too general, too high level. It's you cannot really use it. Okay, the system shall use fast Fourier transformation to calculate signal values. Yeah. So this describes the solution and not the problem. And the requirements must focus on the problem. Actually, I talked with many people from the automotive industry, and they said that in many cases their customers just provide this kind of requirements, and they just, oh no, this is not your task. We will do. We know how to do it. You just have to tell us what you want at the end. The system shall continue normal operations soon after a failure. What is the problem with this? Can you help me? Actually, the problem here is that it is very imprecise. So instead of using soon, you just say that maybe in 5 minutes, 5 nanoseconds, or 5 days. So this soon is not precise. You cannot use it. But if you use some measures, you define it precisely, then you know how to implement it. Sensor data shall be logged by a timestamp. What is the problem with this requirement? I will go up and choose somebody there. I have an idea. Can you help me? The problem is that I told you that the passive sentences should be avoided, and this is a passive sentence. It doesn't tell you who should do that, and then an unauthorized personnel couldn't access the system. What is the problem with this requirement? I told you that you should use specific auxiliaries, and this couldn't, it's not in the specified auxiliaries. Because why couldn't? Because he or she must not, or for other reasons. So use the specific auxiliaries. And it's very So it's very important to find missing and inconsistent requirements in your requirements model, but it's not easy to do actually. So there are some tools that support this kind of analysis, but it is done mainly by the engineers. So they go through the requirements and try to identify these kind of problems. So, and you really have to go through and review your requirements. It's very, very important. And SysML provides some modeling support to define your requirements, and that is the requirement diagram. Actually, requirement engineering has a long history. At first, the requirements were formulated textually, for example, by using Word documents. Then they were handled by requirement management tools, such as these doors that provide this table format to represent your requirements. And the problem is that requirements are very, very complex. So for example, in the automotive industry, it's very easy to get thousands of requirements. That's huge amount to handle. So we need something to support the management and the complexity of requirements. And for this purpose, SysML introduced the requirement diagram formalism that is not in UML, unfortunately. And the main goal of requirements diagram is to answer these questions. So what are the main textual requirements, and what is the hierarchy of the requirements? So it's very, very important. And requirements are organized by these diagrams, and each requirement is represented by this notation. The requirements have their name, they have an ID. Maybe from the last row you don't see it. And there is a textual description. And what is very important is that we can decompose the requirements by using this notation. So this way we can organize our requirements hierarchically. And by decomposing the requirements, we can reach the granularity that you can trace back to your implementation. And the concept of traceability is the following. Actually, the certification and the traceability concept is the core for certification, especially in safety critical systems. So we define forward traceability that tells you that from each requirement how you can reach the corresponding lines of source code. So you will trace your requirements to the source code, and it will show you the responsibility. So you will traceability will lead from a requirement to the source code, and that's the forward traceability. And backward traceability will define you that the lines of the source code which is the corresponding requirement. So this way you can show that there is no extra functionality in your software. So forward traceability is to show the responsibility. Backward traceability is to show that there is no extra functionality in your system. And it is required by many, many standards. There are various relations between requirements. There is a trace relation that is a general relationship between requirements and any other model elements. You can use the refine relationship and relation that depicts a model element that clarifies a requirement. Typically, it will lead from a requirement to a use case or a behavior. The derived requirement represents that, shows that a requirement is derived from another requirement by analysis or by some kind of decision. So as you remember, for example, from the high level requirements, we just created we created additional requirements by derivation. So this derived relation can represent this kind of derivation, and it is used typically between the different levels of hierarchy. You can use the copy relation that supports reuse by copying requirements to other namespaces. It has a general master-slave relation. The satisfy relation depicts a design or implementation model element that satisfies the requirement. And verify relation is used to depict a test case that is used to verify a requirement. And if you have a detailed requirement design, then the goal is that finally you will reach a fine granulated requirement design that where for every low level requirement you can verify them with a test case. So it is suggested, it is advised to reach this kind of granularity in requirements engineering. And I will just show you some examples. So for example, here you see example for the derive requirement. So we have the requirement that the vehicle shall accelerate from 0 to 60 miles per hour in less than 8 seconds under specified conditions. So we can tell that the maximum engine horsepower shall be greater than some value according to the weight of the car and everything else. So this is a kind of derivation. You can use the refine relation between requirements and use cases, and you can still further refine your use cases, for example, by activities. And here you can see a more complex example for the derive relation. Actually, we have an environment condition that the controller shall endure the environmental conditions, and from this we decomposed it. That says that the temperature in case of direct sunlight, and so the controller shall operate in high temperature up to 80 centigrades. We have another customer related requirement that will tell you that the controller shall endure 70 degrees for 4 hours. And by analyzing these two requirements, you can derive the requirement that the controller shall endure 80 centigrades for at least 4 hours. So this is reached by some kind of analysis. And also we can attach rationale to explain why we decided to have this requirement. And here's also an example for how traceability of requirements works in SysML model. So we have the requirements that are defined by use cases, and the requirements are implemented by block diagrams. So these block diagrams will satisfy our requirements, and we have test cases to verify our requirements. We can attach one or more test cases to our requirements with this verify relation. And as I mentioned you, we have this requirement diagram with all the decomposition, and it supports, it helps you to design your requirements, but you can have also this table format, and they are quite the same. But for actually, it's much easier to overview a visually represented requirement diagram. So that's why it was developed. But you can also put your requirements into tables, and you can also provide these relations. So you can depict the hierarchy by using hierarchical numbering, and you can provide traceability links also to your requirements. So you can mainly represent them in this requirement diagram format, or you can use also this table format to store your requirements. And the next step in the systems engineering process is to somehow model system functions and interactions with use cases and use case diagrams. Use case diagrams, you can find them as a form of behavioral diagrams, also in UML and in SysML, so you can use them in both languages. And at first, you want to define that who will use the system, and you use the context diagram for this purpose, where you have the system, the boundaries of the system, you have the external entities, and incoming, outgoing information and control flow. And you can draw it on a whiteboard, or you can use use case diagrams for this purpose. So here you see that we have actors. We can define information flow between the actors and our system. We can represent external systems, actually, as boxes. The box can represent nearly anything. For example, sensors. We can represent actuators and also environmental effects. So in systems engineering, all these things are very, very important. So use cases, if you have the context, the system context, then by using use cases, you want to answer the question, who will use the system and for what? It's also very important that we not only identify that who will use it, but for which purposes. And here you can see the primary actor of our system, that is actually a client, that will participate in use cases. Use cases are inside the boundary of our system, and the actor is outside. So here you can see the system boundary. And sometimes our system also uses some services from secondary actors being outside of our system. So a use case captures the main functionality of the system, mainly corresponding to functional requirements. A use case describes the typical interactions between the users of a system and the system itself by providing a narrative of how a system is used. And the use case can be considered as a set of scenarios tied together by a common user goal. And we usually give them a name with this following language template that is built from a verb and a noun, and it must be unique. So for example, a use case can be drive, train, switch, turn out, listen to my presentation. So all these are use cases. And for use case descriptions, we can also provide some preconditions that must hold for the use case to begin. We can provide post conditions that must hold once the use case is completed. Use cases have a primary flow, the most frequent scenarios of the use case. Let's call the main success scenario. And you can also define alternate flows that are less frequent or not successful, not so successful cases. And you can also add exception flows that are not in support of the goals of the primary flow. And you can further elaborate use cases, for example, with the help of activity diagrams, where you can also provide control logic, or you can elaborate them with the help of interaction diagrams, because these use cases result from some interaction with the system, and you can use interaction diagrams to describe these scenarios in more detail. And actors, so we defined use cases, but we have to define actors. Actor is a role that a user plays with respect to a system. The primary actor invokes the system to deliver the service, and the secondary actor is someone or something that the system communicates with it where carrying out service. That is very important, that the actor is outside of the boundaries of the system, and its characteristic is that, for example, one person may act as more than one actor. As I mentioned, you actor is a role, not a single person. So that's something you have to take into account when you define your actors. And it can also be an external subsystem and not a person. Here you can see that we have the actor of client that will that have this association with the transport cargo and monitor terrain position. And this association means that the primary actor initiates, or the secondary actor participates in an interaction with the system. They use some service of the system. And a use case may be performed by several actors, and an actor may perform many use cases. So the client can transport cargo and monitor train position, and also a use case can be associated, can be used by several actors. And sometimes we have to organize our actors, and you can use generalization for that. So here you have a railway staff, and a railway staff can be a train driver, a railway worker, or the railway operators. So they are all railway staff members, and you can use generalization for this purpose to define this. And this way, for example, you can define some kind of access control, and here any of these lower level, so any sub-actor can perform the use case that is associated with this actor. But if we associate a use case with this railway worker, then that will not be, it cannot be used, for example, by the other actors. And sometimes we have to handle complex functionality. So for example, transport cargo can mean that we have to operate turnouts and drive train, and we can extend actually, or we can include this transport cargo. We can include some other use cases. So the transport cargo includes the operate railway track elements and also drive train use cases. And here now the transport cargo is the base use case, and they are called the included use cases. So this way we can break down a complex core functionality into more elementary steps functions. We can also use generalization between use cases. So that is also called inheritance, that the transport cargo can be transport hazardous material or transport food. They are both they are both transport cargo use cases. So you can use generalization also here. But you can also ask the question, what happens if the selected route of transportation is blocked? So we also need some kind of extensions and to handle not normal behavior of our system. And we can use this extend notation. For example, here, if we cannot, if the route is blocked, then we will find alternate routes. So this way we can extend the core functionality with some unusual situations, some exceptions. So just to overview the use case relations, so we can have associations between actors and use cases, and we use them to show that an actor initiates or participates in some use of the system. We can have generalization between actors or use cases. That means that a use case or actor is more general than another use case or actor. We can extend, we can break down complex behavior, and we can use the include relation when a complex step is divided into elementary steps. And we can use also the extend relations between use cases, and we can add exceptional situations. And also use cases support traceability, so we can use use cases to refine requirements, and we can use use cases to refine system context description. And use cases can be further refined by activity diagrams, or use cases can be implemented by blocks in a block diagram. So in this case, they will satisfy the use cases. And there are some good practices for use cases. So when you group use cases, you have to identify functional building blocks, and you can group your use cases according to this information into packages. And actually there are some other best practices that you should keep actors in a package within a subsystem that they belong to, but I think it's quite trivial. And it's very important to name actors according to their roles and avoid using job titles. And you can also divide complex roles into multiple actors, and start the diagram by placing the most important actor in the left top corner. And when you design your use cases, use domain-specific verbs and avoid technical descriptions. And relationships, actually use extend and include relations lightly, because they can make your use case diagram very difficult to understand. So we saw how to define requirements. We went through the concept of traceability. We defined use cases, actors, and how we use them on diagrams. And tomorrow we will continue with structural description. We will learn how to use blocks, classes, class diagrams, and various other structural modeling languages in system design. So we will continue tomorrow. Thank you very much for coming today, and I hope we will meet tomorrow. And if you have any questions, I'm here and I'm happy to answer them. And if we succeed, actually, maybe at the end of the third day, we'll be in a laboratory and we can have some practice and experience with one modeling tool. We won't develop system models, but we will just practice some behavioral modeling on Wednesday, hopefully. Okay, thank you very much. See you tomorrow.